Hello everyone, I am Aida Vidal-Balea and I am a researcher at the Joint Research Unit with Navantia and PhD student at the University of Coruña in Spain. Today I am presenting our work called A Collaborative Industrial Augmented Reality Digital Twin Developing the Future of Shipyard 4.0, done in collaboration with Navantia Shipyard. And I would like to thank EAI for this opportunity and also my colleagues for their contribution to this paper. The agenda for this presentation is the following. First, I will explain the motivation and the objectives of this project. Next, I will talk about the communication architecture, explaining all the elements that compose the architecture. This will be followed by the design of the system, where all the modules which are part of the system will be listed. Finally, I will talk about the conclusion and present some works that will be carried out in the future. So we will start by explaining the motivation and the objectives of this project. This work presents the development of a collaborative application for Microsoft HoloLens 2 that allows the operators of a shipyard to interact with a virtual cooler during the maintenance process of the real element. For this purpose, an augmented reality experience was designed, which acts as a virtual guide while the different parts of the cooler are being assembled. The motivation for carrying out this work lies in the fact that over the last few years, shipyards are upgrading and integrating new technologies into their manufacturing process, leading to what is known as Industry 4.0. Among these new technologies is the augmented and mixed reality, which provides an improvement during the industrial processes, allowing the creation of new learning and communication systems in real time that achieve a significant reduction of errors during the assembly and maintenance processes of the part. The specific objectives of this project are the following. The first objective is to visualize a 3D model of the cooler with animation sequences step by step, illustrating the maintenance process. In addition, it will be possible to consult the documentation associated to each step. This additional information can be formed by text, images, charts, or buttons, for example. The second objective is the integration of the system with IoT elements. The purpose of this is to connect the application with the digital twin system so that the information can be viewed and interact with in real time. The last objective is to create a system of shared experiences where two or more users can view and interact with the cooler simultaneously. This will add a new way to improve the learning process, since the instructor could be watching in real time what the operator or student is doing and give the necessary indications for a correct learning process. Now I will explain how we created the communication architecture and its parts. Here we have the communications architecture, and as it can be seen on the diagram, it is formed by 3 modules. Each one of them is represented by a different color. The industrial IoT layer is composed by the different sensors and actuators that comprise an industrial IoT network. It can be physically located in the same area where the augmented and mixed reality visualization application is running, or it can even be in a different location. Then, the augmented and mixed reality layer is composed of the end display devices, which can be smart glasses or tablets that users utilize to visualize the 3D information and animations, and to interact with the additional information provided by the industrial IoT system. The last one, the service layer, is in charge of coordinating all the processes as well as managing the different protocols used by the heterogeneous devices. It consists of 3 subsystems: Industrial IoT Service, anchor sharing service, and the visualization system. The Industrial IoT service is in charge of the communications and management with the Industrial IoT layer. It makes use of the MQTT API through an MQTT broker called Mosquito. It handles requests related to Industrial IoT data and commands coming from the augmented and mixed reality devices through the HTTP API. If it is necessary to forward the request to the Industrial IoT layer, it is also in charge of the translation and adaptation of the requests between the augmented and mixed reality layer and the Industrial IoT layer. It also takes care of the persistence of the sensor data thanks to a MongoDB database. The Anchor sharing service is the service that manages shared augmented and mixed reality experiences, ensuring that all devices use the same environment tracking information. To do this, it is necessary to share some data packets called anchors among the devices. These packets are generated on an end device and contain the spatial information necessary for any other device to be able to recognize the environment and to position itself in the same spatial reference system. The anchor sharing service also manages the persistence of the anchors and the distribution of each one to the corresponding devices through the RSTI API. Finally, the visualization system consists of a control panel that allows the user to visualize the status of the system and the active anchors and sessions at any given moment in time. The following section is the design of the system, where I will describe the three modules that form the developed application. The first module is the visualization of virtual objects. In this application, 3D models can be aligned with the real world using user-friendly gestures. These gestures can translate, scale, and rotate the 3D models, as it can be in the video, allowing the user to place the objects in a more convenient spot for its real case scenario. In addition, the system also provides a step-by-step animation display system. These animations illustrate the assembly or maintenance process of the parts, which can be very thorough and contain as many steps as necessary in order to obtain a dynamic manual that can be displayed on an augmented reality device. The application also provides information and warnings associated with each step. This includes images, graphics, charts, and information panels to help operators to check and confirm actions before proceeding to the procedure. All this system allows the user to quickly learn and improve the industrial processes, leading to fewer errors and accidents during assembly or maintenance processes in workshops. The second module is the integration between augmented objects and the real cooler, leading to a digital twin system. As an example, the video shows the implemented virtual panels and display real-time information from the Industrial IoT sensors located on the real cooler. As it was previously mentioned, the Industrial IoT layer is responsible for interconnecting the augmented reality smart glasses and the IoT devices. In order to be compatible with other applications and sensor networks, it uses a secure communication system based on HTTPS. The Industrial IoT service can be deployed in the cloud or using cloudlet. For example, powerful local computers that act as edge computing devices. This helps by reducing latency times, as the services can be placed closer to the client, and in scenarios with a large number of connected devices, It helps to reduce the amount of traffic generated to the cloud servers, as data can be pre-processed or aggregated by cloudlets before it is sent to the cloud. Finally, the sharing system was added, allowing several users in the same location to interact with the application at the same time, as it can be seen on the video. All users share the same spatial reference system, so that all virtual 3D objects are aligned with reality, and at the same time they are synchronized among the different devices. This means that if one user moves the 3D model, it will be moved instantaneously in all the devices that share the same experience. In the final section, I will explain the conclusions and talk about the future work. The proposed augmented reality application was designed and tested for training and assistance during the maintenance of shipbuilding parts. The developed functionalities allow to visualize in detail the virtual elements in real size, placed in the precise way in the position where the real elements would be integrated. After describing the proposed communications architecture, the implementation based on Microsoft HoloLens smart glasses was detailed, including the industrial IoT integration that led to the development of the digital twin system. In addition, the proposed application allows the training and assistance task to be collaborative, thus accelerating the maintenance and manufacturing processes within the shipyard. Finally, regarding future work, it will be focused on improving the interaction with the IoT system for the augmented reality application. In addition, some experiments in terms of usability and user performance in industrial scenarios will be carried out, as well as security and network performance of the different protocols used in the system. These were the main points that I wanted to highlight in this presentation. I thank everybody for your attention and also thank you for the opportunity to be able to present this paper on this conference.